So this short recording will be on how wheels turn on surfaces. So this stuff is quite interesting, rotational dynamics. This is about how wheels, and by wheels I mean rigid wheels, turn on surfaces. So let's draw something out. Let's say we have a flat road and we have a wheel like this. This is not a very good drawing because this should be a point contact. So let me redo it. Let me maybe start here and go like this. Oh, come on. There we go. That's better. And let's say this point here is point P. And this is a rigid wheel. So when I say rigid wheel or rigid disc, whatever, it literally means that there is a point contact at P. So this is different from your regular automobile tire, if you will, because the part of the tire that touches the road is quite flat. That would be a more complicated scenario, which we won't do here. So let us say that at this point, I take this as the center of the wheel, and I draw, let's say, the radius here. So this is R. And the wheel has a mass M, as usual. And let's say that about this point P, I consider a rotation of the wheel. So the wheel hasn't really moved. It is just tending to rotate. And as it tends to rotate, if you will, the edges of the wheel will have velocities like these, tangential to the surface of the wheel. So you can see that this stuff is not simple. The rotation of the wheel is a fairly complex problem. If I now follow through with the idea of the rotating wheel, then what happens is that down the road, the wheel ends up, let's say, around here somewhere. And let me call this position Q. So this point is Q. And then the original radius line, which imagine this is an actual line. So let me give it a color. This is an actual line I have drawn. Okay. So this line in the wheel is now sitting, let's say, here, center. And if I, and this was the original position at P. So if I want to analyze this, the wheel has turned by this angle, let's say delta theta. And this distance here, I can call it delta x. So at this point, I should be able to say that the linear distance the wheel travels, let's call it delta x. So this is displacement. Delta x must be equal to r times delta theta. So this, by the way, is also a no slipping scenario, right? And if I now make delta x over delta t, this quantity would be the velocity, and the velocity would be r times delta theta over delta t, and this would be r times omega. What is this omega? This omega has to do with the angular velocity or angular speed with which this wheel is turning. And what is this V? Well, we have to be a little cautious here, because if you notice this delta x that we have here, this delta x is displacement. And therefore, delta x over delta t is the velocity, but the velocity of the center of mass. So in other words, if the wheel is going from point P to point Q, the velocity we are talking about is this velocity, V, center of mass. So we are talking about some interesting issues. One is the fact that at point P, there is a point contact. The wheel is beginning to turn. As it begins to turn at that instantaneous, the instantaneous analysis would yield velocities like I have drawn here. And then if you let it actually go from P to Q, it covers a distance of delta x from left to right, that's a displacement, and that's equal to r delta theta. Delta theta is the amount by which this red line that we have marked up on the wheel turns, and that turns out to be connected with V center of mass. Now, for you to have a point contact, there must be static friction at P. If there is no static friction at P, then the wheel will not be able to have this no slipping contact at all. It'll slip. And so therefore, the center of mass will not be moving forward like we see here. So I'll come back to this point because this turns out to be an important point to keep in mind. We now want to find out what is the kinetic energy of the wheel. So we ask this question, what is the kinetic energy of the wheel? Before we do that, let me sidestep and go back to a discussion I had with you earlier. In the lecture I gave on April 1st, I told you about something called the parallel axis theorem. I didn't spend a lot of time on it, but now I'll go back and use it for my own advantage. Let's say I have a disk like this. And let's say this is the center of the disk. And I have a vertical axis that runs like so. And the wheel is turning. So it has some radius r. And C is this point, and M is its mass. So I can say that the moment of inertia of this disk about its axis passing through the center, mark my words, moment of inertia I about the axis passing through the center is 1/2 m times r squared. Again, because it's a disk, as I told you. The idea of parallel axis theorem is as follows. Suppose I draw the same thing. But now instead of having this line at the center, the axis at the center, so the axis is no longer at the center, I actually make the axis here, let's say at an edge. This was C, let me call this P. And because it's at the edge, this distance here is R. And what parallel axis theorem tells us is that the moment of inertia of this disk I about P is the same as the moment of inertia about C, which is 1/2 mr squared, plus m times r squared, where r in this case is this distance. Now, if this distance is not r, but something else, let's say d, then it would be m times d squared, okay? All right, great. So let's now see if the parallel axis theorem will actually help us as we try to estimate the kinetic energy of the wheel. The kinetic energy of the wheel, Ke of the wheel, about point P, let me call it Kep, is equal to 1/2 the moment of inertia IP times the angular speed omega square. That's what I would think is what you would want. So let me now make some space. I'm going to pull this part of the discussion down. Let me get it down here. It's a nice feature of the iPad. Let me now go back and try and rewrite this part here. Oh, sorry. Here, rewrite this part here. So what I'll say is I'll write Ke P of the wheel is equal to 1/2 m r squared, right? Plus 1/2 m r squared times omega squared. Now this 1/2 mr squared, by the way, comes in only because we are dealing with the disk. So in general, suppose it's instead of a disk, it's a sphere or something, we can make it more general. So generally I can write Ke of the wheel, sorry, is equal to 1/2 mr squared plus the moment of inertia about the center IC times omega squared. So therefore I have 1/2 m times r squared omega squared plus 1/2 I about the center times omega squared. Now, if you recall, this r squared omega squared is nothing but the center of mass velocity. And so therefore, this thing turns out to be 1/2 times mass times v center of mass squared plus 1/2 times I about the center times omega squared. The important point here to notice is that it's as if the first term, this term here, describes that the wheel is simply translating forward. So it's like the wheel here is simply translating forward and not even turning. And the second term here describes that the wheel is simply turning, but not even translating. So in a sense, the kinetic energy of the wheel about the point P can be broken down into these two pieces. I will now quickly do a simple problem. So in this problem, let me switch over to black and let me do this because I'm going to draw an inclined plane. Oops, like this. And let me have a disk here. And let us say this is at some height h. Okay, so like this. The mass here is m, and the total energy initially is mgh is the energy at B, and from there, hopefully calculate what would be V final. So in other words, I let this thing go, and as I let it go, it starts to roll, and as it rolls, it speeds up. So the energy at B, based upon what we have just learned, is going to be 1/2 mass times V final square. I don't know what V final is, plus 1/2 I times omega final square. And because there is no slippage in this case, we shall be able to write V final is R times omega final. So therefore, I can write mgh is equal to 1/2 mass times V final square plus 1/2 I. But I is always of the form of some beta, beta being some number, times mr square, and then V final square over R square. That is just replacement of this omega final square here. Beta is some number. So for disk, you have beta equal to 1/2. For sphere, you have beta equal to 2/5, etc. All right. So now you can immediately calculate what V final would be. First of all, let me take the liberty of canceling out the big mass, because the big mass doesn't matter. R squares cancel out. And so I'm able to write GH is equal to 1/2 V final square plus beta over 2 V final square, which would basically be 1/2 V final squared times 1 plus beta. So therefore now V final is going to be 2GH, 1 plus beta to the power of 1/2. In one of the bonus quiz problems, I asked you if I took an aluminum cylinder and a lead cylinder of exact same dimensions, whether they would reach at the same time. It'll turn out that the mass wouldn't matter. So the final velocity would actually be the same, which would mean that they would indeed reach at the same time. However, some of you answered it will not reach at the same time, and some of you answered it will reach at the same time. In reality, it will not reach at the same time because of friction and air resistance. The times would be very slightly different. If you do it in vacuum, they should reach at the same time. I decided to give credit to whoever answered this question correctly or incorrectly. So no point was lost. But I did want to work this problem out completely for you, just so that you guys feel like you understand, hopefully, the material. With that, I'll close this session.